All right, so today we're talking about periodic trends, and we're going to be doing some introductory organic chemistry. Don't let that scare you off. You're not going to actually do real organic chemistry. You're just getting introduced to organic chemistry. Hi, how are you? So we're going to talk about periodic trends. These are things that are in the periodic table. That's why they're called periodic, because they come from the periodic table. And these are patterns so that you don't have to memorize every detail about every element. You can just look at the periodic table and you can have a general idea of some of the properties just based on where they're located. And some of these we've already talked about, but let's just review. All right, atomic radius decreases as you go across the period and increases as you go down a group. These two are always going to be opposite each other, okay? For all of these. If it's decreasing one way, it'll be increasing the other way. All right? And so when you think about that, if we're drawing atomic nuclei, right? So here would be the nucleus, and then here's my one electron if we're hydrogen, right? And then if you add more electrons for helium, lithium, beryllium, etc. All right, so the reason for this is called effective nuclear charge. That's what we call that, okay? Effective nuclear charge. As you go across the row, you have more electrons, but you also have a greater charge on the nucleus, right? Because you're increasing number of electrons, you're also increasing number of protons, right? So what does effective nuclear charge tell us? It tells us that as the charge on the nucleus increases, electrons are pulled in tighter, is I guess the best way to think about it. Right? Because if you've got a more positive nucleus, right, then the protons are significantly larger than the electrons, right? So as the charge on the nucleus is getting bigger, those electrons are getting pulled in tighter, okay? And that's why the radius decreases going across the period. Does that make sense? There's another thing that you need to add to this section. I should have written reason/examples, because we also need to talk about cations versus anions. Cations, have they lost electrons or gained electrons? They've lost electrons. So, would you expect them to be bigger or smaller than their parent atom? Are smaller, yes. Okay, so in other words, so for example, Ca2+ is significantly smaller than calcium metal, right? Because the only difference between calcium ion and calcium, they have the same number of protons, right? But there are two fewer electrons, so that electron field is smaller, so that whole radius is smaller, because they've got the same number of protons. So you can't really look at proton side. You're looking at the electron cloud. It's smaller because you've lost two electrons. What about anions? What would you expect for them? Have they lost or gained electrons? They've gained. So are they bigger or smaller? What would you expect?
Bigger.
They're bigger, yes, than their parent atom. All right, so for instance, bromide is bigger than bromine. All right? Think about why. They both have the same number of protons. So it's not protons that's the driving factor here. It's the size of that electron cloud. Right? Bromide has gained an electron, so it's a bigger atomic radius than bromine. Does this make sense? All right, so for instance, if I said, where's a blank periodic table? If I said, all right, who's bigger? And you've got a periodic table on your handout. Who's bigger, sodium or sulfur? Look at your periodic trend. Who's bigger? Sodium will be bigger, right? Because what happens? It's decreasing across the period. Sodium and sulfur are both in the same period. Sodium is bigger. What if I said, who's bigger, beryllium or barium? Barium's bigger, right? Because they're both in group 2. So do we understand how to interpret this? Yes? Okay, any questions on this periodic trend on atomic radius? All right. Let's move on to the next one. Let's look at ionization energy. Okay, so the reason for ionization energy is the same as the other one, effective nuclear charge. And ionization energy stands for energy required to remove an electron. Okay, and we're talking about here the energy required to remove an electron to make an ion, essentially. Okay, so ionization energy is going to increase across a period and decreases down a group. Okay, so the reasoning is the same. It's effective nuclear charge is the reason. I didn't give you space to write the definition of what ionization energy is. And here's another thing we need to add. So like I said, call this reason / extra info. The first ionization energy is always less than the second ionization energy, which is always less than the third ionization energy, et cetera, et cetera, et cetera. And I've got a figure that I wanted to show you. It's in a PowerPoint here. So let me. If you look at ionization energy trends, and this is a figure from an old textbook. So if you're looking at first ionization energy versus second ionization energy, look at sodium. This is the first ionization energy, all right? Why this humongous gap here? My goodness, that's a huge gap, right? It's like it almost increases 10 times. Think about sodium. When you form sodium, what's the charge on its ion? This is the charge, this is the, what would that be? Na with what charge? Plus, right? So second ionization energy, what cation would that be? Na2 plus, right? You're removing, here you're removing core electrons, whereas here you're removing valence electrons. Okay, that's the difference here. That's the difference. Removing valence electrons takes significantly less than trying to remove a core electron. Okay, and that's the same thing here. So here's magnesium. There's forming Mg+, there's forming Mg2+, but look what happens when you try to form Mg3+. I mean, that's just insane, right? That's an insane amount of energy. Because those core electrons are the ones that are closest to the nucleus. They are the ones that are like, we're not going anywhere, right? Valence electrons are the ones further from the nucleus. They're more easily removed. These guys, and you see the same trend going on, right? The same trend as you try to remove core electrons, these are all equivalent to removing core electrons, right? It's just going to become nasty. So that's the part of the reasoning behind it too. And that's really all that I want you to deal with ionization energy. And we're only looking at first ionization energy. That's the trend in the periodic trend. All right, you actually already know electronegativity. And we've talked about that one quite recently. What happens to electronegativity as you go across a period? It increases. And down a group, it decreases. And this is the same reason. Okay, it's effective nuclear charge as well. It's really the same for all of them. I'm just rephrasing it. Do you remember which element is the most electronegative? Fluorine. Fluorine's most electronegative, right? Again, the charge on the nucleus is increasing. Those electrons are being bound more tightly to the nucleus. And if they're being bound more tightly, they're not going to share very well. So if we've got our periodic table here, which I have for you, there's periodic table. If you want to summarize your periodic trends, going this way, What happens to atomic radius? Going left to right. Increases or decreases?
Decrease.
What about ionization energy? Look at your handout.
Increase.
Increases. What about electronegativity?
Increase.
It increases. And then going this way, it would all be the opposite. Right? That's nice because if you remember it one way, you just know it's the opposite going the other way. So let's take a second and do a couple of practice problems just for fun. And I'll stop the recording and give you time to work on these. Number 1, rank by increasing first ionization energy. Let's do vanadium, zinc, bromine. And then 2, rank by decreasing size. Radius is what I'm talking about there. Let's do fluorine. That's set number 1, and then let's do another set. Let's do okay. Do those 2 problems. Use your periodic table. I'll pause the recording and give you a second to work on those. All right, let's go over the answers to these. So we're going to do these first rank by increasing first ionization energy. All right, so we're looking at vanadium and zinc and bromine. So what's the trend about ionization energy going left to right? It increases. So to rank them by increasing first ionization energy, which one goes first? The smallest ionization energy or the highest? Smallest, right? So who goes first? It's actually already in.
I was going to say you wrote it in order.
Vanadium is less than zinc, which is less than bromine. Any questions on that trend?
Thank you for the answer.
You're welcome. All right, now let's do rank by decreasing radius. All right, so we've got fluorine, we've got iodine, we've got bromine, and we've got bromide. So by decreasing size, so what goes first? If it's decreasing size, who goes first?
The biggest.
The biggest. And what happens to radius going down a group?
Increase.
It increases. Okay, so of these ones, who is the smallest? These guys up here, are they smaller or bigger? These are smaller, and these are larger, all right? So who is the biggest since we're doing it by decreasing size?
Iodine.
Iodine's first, and then who's next?
Bromine.
Are you sure? Bromide, right. Bromide is greater than bromine. Why? Why is bromide bigger than bromine? Because it's an anion, right? Anions have gained electrons, so their radius is bigger. And then all of those are bigger than fluorine. Do we understand that answer? All right, and then the last one, we've got lithium and sodium ion and sodium and rubidium. All right, again, we're doing these by decreasing size, so who goes first, the biggest or the smallest?
Biggest.
The biggest. If we're going by decreasing, the biggest goes first, so who is the biggest? Rubidium's biggest. And then, who's next?
Sodium.
Oh, we've got a discrepancy here. Who's bigger, Na plus versus Na? This one has gained electrons or lost electrons? Lost. So who's bigger here?
Sodium.
Sodium is bigger. All right, so who comes next?
Sodium.
Na, then who's next?
And then
Na plus, then who's next? Questions on how we did these rankings? Questions on those rankings? All right. So all you're doing is just looking at the periodic table and applying those trends. All right. All of my markers just always dry out. Especially since I'm trying to get it to record, I want to have a nice dark marker. All right, let's turn on to the back and do some introduction to organic chemistry. And I emphasize the word introduction, okay, because we're not learning about how to name organic molecules. We're not learning about reactions involving organic molecules. We are literally just learning the basics. If you like this, you enjoy this, and you say, you know what, I want to take some more of this, you can take Chem 1124 next semester, which is elementary organic and biochem, and it's a science elective. So if you do another science elective and you don't want to take Chem 2, which I recommend doing as well, you can take elementary organic and see something on the different side of chemistry. All right, so organic chemistry is the chemistry of carbon compounds. Okay, these are all carbon compounds. That's what we're talking about here. And because carbon is the star of organic chemistry, we focus a lot on it and how many bonds it needs. Carbon must have 4 bonds. 4 bonds. Okay? Carbon must have 4 bonds. Single, double, triple, combination of those, carbon's got to have 4 bonds. So when you get to organic chem, you're going to get tired of drawing these dang Lewis structures. Because drawing out all those hydrogens for all these organic molecules can be big. And it's a real pain in the neck to have to draw all those hydrogens. So we use what's called condensed molecular formulas, and then we also use skeleton notation. So to turn, this is just a regular old Lewis structure. To turn a Lewis structure into condensed molecular, what you do is you just break it up into the carbons. What's on the carbon? So this is a CH3. And then CH2, 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 CH3. Now, if you want to draw the sticks in between it, that's fine too. Okay, does everyone understand how we went from Lewis structure to condensed molecular? So another way to write that exact same thing would be CH3 dash CH2, 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 CH3. It's the same thing. Okay, does everyone see how we did that? And now to draw the skeleton notation, when you take elementary organic chem, see I say when, right? Because you're just going to be so enticed by this, you're going to do it. When you take organic, you're going to do a lab where we break out the model kits and we just make models of organic molecules. So you can see where these shapes come from. If you make a model of this, this is the tetrahedral molecular geometry. Ooh, think back to Vesper, right? These are all tetrahedral molecular geometries. So you've got one coming out of the board, one row behind the board, and then 2 in the plane of the board. When you put this together in a 3-dimensional model, it actually takes on a zigzag kind of shape. So to turn this into a skeleton notation, every single one of these carbon atoms is a point on your zigzag. So this is 1, 2, 3, 4, 5, right? 5 carbons, 1, 2, 3, 4, 5. We're ignoring the hydrogens. So carbon, if you want to make a dot to help you visualize it, 1, 2, 3, 4, 5. So when you see this, now those dots are there just to help you visualize it. I would draw it like this, 1, 2, 3, 4, 5. It just looks like a letter M that somebody stepped on, right? Every point or end is a carbon with its appropriate number of hydrogens. So if I said, all right, take this and give me the Lewis structure back, how would you translate this back into a Lewis structure? You just put a carbon on every spot, and then how would you know how many hydrogens to fill in? Right, exactly. Carbon's got to have 4 bonds, so you just figure out, okay, this one can only have 2 hydrogens, right? Because it's already got 2 bonds. Therefore, the other 2 bonds must be the hydrogen. Okay, does this make sense? So what I want you to do is take a minute and try the next 2. Try these 2. I've given you the Lewis structure. You turn it into condensed molecular, and you turn it into skeleton notation. And I will pause the recording and give you a chance to try that. Okay, let's go through these. I'm going to zoom it in a little bit. Okay, now if you take elementary organic, which I hope you do, you'll learn how to name this molecule. You'll learn how to number it and all that good stuff. We're not worried about that right now. We're just looking at how do we condense this down so it's not such a mess. All right, so we've got CH3, CH, then we've got CH3, then we've got CH, then we've got CH2, and CH3, then we've got CH2, CH2, CH3. Isn't that a lot easier to look at than that silly Lewis structure with all those hydrogens in the way? We can make it even easier because we can also turn this into a skeleton notation. All right, so this is a 1, 2, 3, 4, 5, 6 carbon backbone. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And then on carbon 2, you've got a 1 carbon chain, and on carbon 3, you've got a 2 carbon chain. Boy, that's so much easier to look at. And much faster to draw. Everyone see how we did that? This is as far into this kind of stuff that you're going to have to get. Okay, so if you're like, what? Okay, this is as far as we're going to have to get into it right now. And by the way, it's just practice. That's all it is. It's just practice. What's special about this one? It is cyclic, yes, and it's got a double bond in there, right? So we have to be careful about that. Because if you start here at the top and go clockwise, CH2, notice CH, CH. How come it's not CH2? What would happen if it had CH2 right there? How many bonds would that carbon have?
Too many.
1 too many, right? CH2, CH2, CH2. Okay, so there it is in condensed molecular, and then skeleton notation. Just look like that.
Can we not just write it in a straight line like we did the first one?
What in a straight line?
The condensed molecular.
This?
Yeah.
You can't put it into a straight line because this is a cyclic molecule, so it needs to stay cyclic. Does that make sense?
Yeah.
If it's a ring, it's got to stay as a ring. Questions on how we did this one? Condensed molecular or skeleton notation. Are we okay for me to erase?
Yes.
All right. Let's move on to the functional groups. Now the functional groups you're going to have to memorize. I recommend making flashcards. Name on one side, formula or shape on the other side. So functional groups are just areas where organic reactions occur. That's why we call it functional groups. There's a function, organic reaction, that takes place at that part of a molecule. Okay? So an alcohol looks like OH, where this could be whatever the molecule is. Okay? So let's draw a couple molecules that contain alcohols. So that would be an alcohol, right? That would be an alcohol. Notice the carbon atom is not included as part of the alcohol. It's just the OH. Just the OH, right? This is the carbon it's attached to, but this is the actual functional group. This is the carbon it's attached to, but this is the actual functional group. Okay, so that's the alcohol. That's the carbon it's attached to. So don't include that carbon. If I gave you that molecule and said, circle the functional group, make sure you circle just the OH, not that carbon atom. Carbon atom is not part of the functional group. Okay, it's just the OH. Make sense? So it's very likely that I could give you on the test a molecule and say, circle and identify all the functional groups. You would circle OH and write alcohol beside it. Okay. Aldehyde it does include a carbon atom. Okay, that's why we make a point of differentiating that. C double bond O H. And this is the rest of the molecule. Okay, so in skeleton form, an aldehyde would look like this. How come there's no H right here? Do we put hydrogens in skeleton notation? Are there any hydrogens drawn in skeletons? No, you have to visualize it, right? If you saw this, you'd say to yourself, okay, how many hydrogens are on these atoms? 3, 2, 2, 2, 1, right? You visualize it. And so the carbon is part of the functional group. Or if you had there's your aldehyde. Okay? Does everybody see how to recognize aldehydes? They are on the end of the molecule. If we were to put an aldehyde on this guy that we just drew a second ago, that would be the aldehyde. Make sense? Everybody good on aldehyde and alcohol? Yes? Okay, let's look at amine. There's so many puns you can make with amine. Amine. So amines can be either that, or they could be that, or they could be that, right? This is just number of hydrogens. That is amine, that is an amine, that is an amine. A tertiary amine, a secondary amine, or a primary amine. You don't need to know the difference, but they're all amines, okay? This one we call a primary amine. This is called a secondary amine. This is called a tertiary amine. You don't need to know that for a test. You just need to be able to identify an amine, okay? So if you had this, that would be an amine. I mean, there are lots of variations you can come up with. So if you want to make an amine right here, that would be an amine. Right? If you want to draw a tertiary one, there's a tertiary amine. Okay, so all of those guys would be amines. So what would you circle? Just the NH or the NH2 or just the N. Again, you don't need to be able to know which one's primary, secondary, or tertiary. Just be able to recognize it. Okay? Ether looks like that. It's just oxygen in between two other things. So if you had this, that would be an ether. You could have, that would be an ether. Right? So you could have anything, any combination of something on the left, something on the right. Okay, that's what an ether is. Everybody good on ether? All right. Let's do ketone and carboxylic acid. Those are the last ones you are responsible for in this class. Ketone is analogous to an aldehyde, but the difference is an aldehyde has an H, whereas a ketone is just the carbonyl. Remember this C double bond O, so it's just called a carbonyl. Okay, so if you had a ketone, it could be here. Where would an aldehyde be? Aldehydes are always on the end. So if it were on the end, it'd be an aldehyde. But since it's on the middle, it could be a ketone. That would be a ketone. And then the last one, I saved this one for last because students always mess it up. A carboxylic acid looks like this. Students mess this one up because they'll say it's a ketone next to an alcohol. And that's not correct. This whole unit is called a carboxylic acid. Okay? So a lot of students will split this up. They'll call that a ketone and that an alcohol. And I'll say, wrong, sadness, right? Because when they are together, that unit is called a carboxylic acid. So if you had this, that would be a carboxylic acid. Okay? There's benzoic acid. You see that a lot of different places. Okay? So what we're going to do now is I am going to draw some molecules. We'll do like what it would be on a test. I'll draw some molecules, and you will circle and identify the functional groups. Go on to our new sheet of paper here. Get that cursor out of my face. All right. We're going to do two things. Part one, circle and identify the functional groups. And then in part two, add the following to that molecule. So I've given you the parent molecule, you add these functional groups to it, and then here I'm going to draw some molecules and then you circle and identify the functional groups. So I'll get you started on these. Add a ketone. Add an ether. You can get creative on how you do this. Add an amine. Add a carboxylic acid. Add a, what else do we do? Alcohol. And add an aldehyde. So you'd have to probably draw 6 different molecules. I mean, maybe you could find a way to make it work. But that's what I want you to do. All right, here, let's see. Okay. 3 to do for circling and identifying, 6 to do for adding to the parent molecule. I'll give you a few minutes to work on this, and then we'll go over it. see how we did. So let's start with our identifications. What functional groups are in number 1?
Amine
Amine, yes.
and
What else?
ketone.
Are you sure that's ketone?
No, aldehyde.
It's an aldehyde, right? How do you know it's an aldehyde?
It's on the end.
That's right. Is this anything?
No.
Nope, that's not. Okay, what about number 2? What functional groups do we have there?
Ether.
We have an ether. What else do we have?
Aldehyde.
Aldehyde, yep.
Carboxylic acid.
Yep. And carboxylic acid, good. Anything else? That's it. All right, what about number 3?
Alcohol.
We have an alcohol.
And amine.
One amine.
Two amine.
We got 2 amines, right? Both of those are amines.
Ether.
Ether, yep.
Ketone.
Ketone, good. And again, the difference between a ketone and an aldehyde, ketones are on the interior, aldehydes are on the ends, right? End and interior. How do we feel on those? Again, I recommend making some flashcards, right? Just draw ketone on one side and write the name on the other side. They're even, you can probably download those from the internet somewhere on your phone. There are all kinds of apps for that kind of junk now. Okay, if you wanted to, you could put all 6 functional groups on this same molecule. It'd be a busy molecule, but you could do it. If we were going to add a ketone to this, just doing it really simply though, how would we need to position the ketone? Would it be on the end or would it be on the interior somewhere? So if we just did this, would that turn it into a ketone?
Correct.
Yeah, that'd be fine. Or what if you did that? That's not a hydrogen, right? Because if it was a hydrogen, we just leave it off. That's still a ketone, isn't it? Because that's a CH3. This is the rest of the ring. That's ketone too. Right? So if you came up with any variant, so long as your carbonyl is in between 2 carbon atoms, you're fine. Okay? Any questions on adding a ketone here? All right, let's add an ether. There's only one way, really, you could add an ether to this. What's that? I guess there are 2 ways. If you replaced a carbon atom with an oxygen, that would work. You did that. That would work.
You draw like a line off now and then another
If you did that, that would work too. Either way. Any questions on adding ethers? All right, adding amines. I'm going to stand directly in front of the camera. Since I'm right-handed, it makes it kind of hard. Okay, amine. How would you add an amine here?
right off of the NH2.
Okay, you could do that. You could have also made it as part of the ring itself. NH. That would work too. Any questions on how you would add an amine to this? Okay. Carboxylic acid. Okay, line off, and then what?
Double bond to the atom.
Okay, then what?
Another line to the NH.
Right. Is there any way to make this part of the ring? If I put
If you tell me how.
that, is that acceptable? How many bonds does this carbon atom right here have? 1, 2, 3, 4, 5. Is that allowed?
No.
No, that's not allowed. This is the only way you could do it. All right, for alcohol, there's only one way you could do that as well. What's that?
Cool off and put no
Right, so just draw something off to the side.
Christmas spirit there.
Ah, there you go. And last one, aldehyde. Can you make an aldehyde part of the ring if you just did this? Would that be an aldehyde?
No.
No, what would that be?
Be something else.
What would it be?
Ketone.
A ketone, right?
Sorry,
So
I had to find it.
can't be that. What's the only way you can make an
You had to
aldehyde?
draw a line, and then
Has to
double-
come off, right?
Yeah. Then a double bond is now.
That would be an aldehyde. That is a ketone. Did anyone make all 6 on the same molecule just for fun? You could. I mean, it'd be a busy molecule, but you could do it. Any questions on how to identify or draw functional groups? Feeling pretty good on periodic trends and functional groups? All right. That is where we will stop for today.
So